In the previous lecture, we learned in detail how to define the gravitational load. In this lecture, we will be using the same structure and performing the basic general structural analysis. So the structural analysis first involves that we have to perform the analysis and complete the analysis in the structure. Right now we have defined dead load, finishes load, live load, wall live load, roof live load. So we have to click on run on all the load cases. So all the load cases will be run and click on run now. So after the analysis will be complete, we'll be able to see the different results for the 3D structure. Shape of the structure which the software shows itself as soon as the analysis is complete. You can click on start animation to see how the structure is deforming under the applied dead load. So you can click on undeformed shape from here, or go to display show undeformed shape, or simply press F4 as the shortcut is shown here. So this is how the structure was shown undeformed, but you can see the deformed shape of the structure. Please note that in the display tab we can see all the results that are applicable to the structure. Right now these results are frozen because we haven't performed, for example, we haven't performed the dynamic analysis. In the later part of the course we learn how to perform dynamic analysis, but right now we haven't applied the dynamic load to the structure, therefore these results are locked. So we can see object assigns, and these are all the assignment part. This is the load case tree, this is the deform shape. So we can see the deformed shape of the structure due to lead load. Let's say deformed shape due to the finishes load which we applied. You can specify the scale. If I specify scale as 1, then the deformation would be real. That means this is how the structure would be deforming in real life, but this is very less deformation to be noticed on the software. So we have to exaggerate the deformation in order to see them in the software. Even 200 times is not enough to notice on the software. So now 500 times exaggeration is enough to see on the software. You can also draw contours on the object for the deformation in X direction, Y direction, or Z direction. Since finishes load is a gravitational load acting in Z axis, this is the Z axis. I'll see the stress contours or the deformation contours here. While the color scale shows how much deformation is occurring in meter units, you can change the units to millimeter, and this is how wherever we have blue color the deformation is greater than 0.17 millimeter, and where we have purple color the deformation is greater than 2.38 millimeters. The deformation is increasing as we go to the purple side while decreasing as we go to the blue side. Similarly, we can see deformation due to live load. All are gravitational loads, so we are selecting UZ, and you can see the wire shadow as well, which will show us the undeformed structure from the gray line, and we can see the comparison. If you want to see in the plan view, you can go to XZ, XY view. This is the plan view, and you can see the elevation view as well. You can go to set 2D view and see wherever you want to see in the two-dimensional view. So this is the plan view, elevation view which we are seeing. We have the shear wall in center part of the structure, so this is showing the plan view. If I select XZ plane and click on apply, as we are right now seeing the XZ, which is the elevation view. So I have selected on XY, which is this one frame. If we see in 3-dimensional, right now I am viewing this frame, this one. So if I go to view, set 2-dimensional view once again and select this one where we have shear wall here, So we can easily see this one. This is already specifying the offset itself. If I have to see the outer frame, then it has automatically specified the offset as 6 meter or 6000 millimeters. If I click here and close, this is where we are seeing the deformation as well as the contours. Similarly, we can see different results. Let's click on display, forces, stresses and joints. You can see the joint reactions for the dead load, and you can change the units to kilonewton, and this is the joint reaction to the upside as well as the lateral joint reaction. For other loads we can also see the joint reactions. Let's define load combinations. Add default design combinations and click on steel frame. Set combination data, and these are the load cases which we have selected for the load combination. So these are the load combinations defined by the software, and what code the software has selected for load combination you can see from here. Steel frame design, since we have selected steel frame for load combination, and click on view revise preferences. It has selected AISC 360, that is American code. You can change the code from here and define the load combination once again according to your design requirements. Let's see the joint reactions for the first load combination, that is 1.4 times dead load, and this is the load combination joint reaction. Let's see shear force diagram. The shear force diagram is shear 2-2 diagram. Let's say we have to see it for the combination number 1. If you want to see the values of the shear force diagram in the picture as well, click on show values and apply. And this is all showing in the unit which we have selected from here, that is kilonewton. You can increase or decrease the scale factor for the shear force diagram. Or you can set it to automatic. Similarly, if we have to see the moment diagram, we can see the moment 3-3 diagram as well. That the moment 3-3 is due to gravitational load, and moment 2-2 is due to the in plane turning of the frames, while shear 2-2 is due to gravitational load, and shear 3-3 is due to in plane shear acting. Shear 2-2 is substantial as well as moment 3-3 due to gravitational load. And this is the moment diagram which we can see. Let's see the moment diagram for the frame which we had the shear wall. So we can see set 2-dimensional view and click on here. We can also see the shear force diagram in 3-dimensional view as well as in plan view. But right now it's not showing in plan view. We can see shear 3-3 in plan view. As I mentioned, it is due to the lateral loading, but since the gravitational load doesn't have much lateral effect, so these are in very small numbers. Similarly, moment 2-2 is due to the lateral, so it is also very less. You can also see the torsion in kilonewton millimeters as well as axial force. Let's see axial forces in the columns which we can see in the elevation view. So this is the elevation view, and I am seeing the axial force in the columns. You can check other results as well. Let's say if you want to check the stresses in the wall in MPa units. So MPa units is Newton millimeter per second square, Newton per millimeter square. So this is going to be showing in the MPa units. Click on forces, stresses, shells. Let's say I have to see the stresses due to live load. You can select the stress components. We have discussed stress components. Click on apply. So this is showing me the stress components in MPa units, that is Newton per millimeter unit, due to live load. Let's say select it for a combination, and similarly you can see for F22 maximum flexure stresses as well, maximum flexure stresses and minimum flexure stresses, maximum shear force, stress due to shear force, which is 0 right now as no lateral load is applied. FVM means von Mises stress. You can compare it with the strength of the material. Shell stresses, shell strains, and other results you can see from here. You can also see it with deformed shape. The stresses with deformed shape are also being shown here. Click on OK to close the window. That is how we check the results in SAP 2000. You can also see the results in a tabulated form by clicking on Show Tables. Click on Analysis Results, Run Information, Joint Outputs, Displacements, Reactions, joint masses, element output, structure output, base reactions, model information. This is all the analysis part. So click on here and you can select the load patterns for which you have to see the results, as well as the load combinations. You can also export the tabulated data. You can also export the tabulated data to Excel, as this is readable by Excel. So now the tables are available. You can see first table which we selected was the analysis messages. You can also maximize it. Assemble joint masses. This is the joint number and base reactions. Base reaction is the reactions at the bases. Element forces, that is the area shells, and these are the stresses, the maximum stresses in the element. The area text 1 shows the number of area. If you want to see which area is this, you can click on. This is area text 1. If you want to see which area is this, you can click on. First we have to close the table. Click on select, labels, go to area and area 1, select. So this is the area label 1, or you can also see from here. So this is area label 1. Let's see the tables once again. Whether it be joint, area, or a shell element, the selection using labels is same as shown. As right now I selected area labeled 1, the steps remain same for all elements. This is just a tabulated view of the results which we just We have already reviewed this one table. Let's go to element and frames. So this is frame number 1. Similarly, we have multiple frames. The frames show beams and columns. For example, frame number 24 shows multiple loading. For finishes load, live load, wall load. It has axial force, shear force, torsion, moments. Similarly, we can see element joint forces for area, frames, shell elements, joint displacements. Let's say for joint number 5, the displacement due to finishes load in u1 direction, that is x direction, y direction, z direction, rotation in x direction, y direction and z direction in millimeter and radian units. Similarly, joint reactions. This is joint reaction F1, F2, F3 and 0 moment. Since we have pin supports in the base of the structure, we will discuss in detail modal analysis in later part of the course. And similarly, we can see other similar forces. This is the structure analysis or the joint length option. This means that the element 1 consists of a joint at node number at 9000 millimeter and 6000 millimeter and so on. This shows the nodes of the multiple elements. So this is how we can perform structure analysis in SAP 2000 for basic gravitational load. In later part of the course, we'll discuss how to define the seismic load and wind load and see the